Okay, we're starting our very last section on exponential growth and decay. A primary use science. We call it carbon dating, and they did a whole bunch of practice drills to come up with this equation right here, this formula, I should say. And notice it is restricted to uninhibited. In other words, that nobody has added something or taken away the environment in which it exists. We use it in archaeology and we use it in science to figure out what will kill the bugs. We can't kill all the bugs, but we definitely want to know when it will reduce to a manageable amount. Like I said, you run into this model, that's a good word. So it says A of t, the amount of t regarding time is the original A sub O and I'm going to say amount because sometimes it's weight, sometimes it's quantity, so amount. And then, of course, we have E, which is our irrational number, not only in finance, but in science, raised to K, which is the percentage or the constant. T, and T is time, measured in time. And we use it for doubling, we use it for all kinds of things. So this model here is cells, specifically cells. And that's why I don't like this book. This is it for the whole course, the whole lesson. But then they specialize it. And I'm not sure, I haven't seen the science textbooks that change the capital letter in front, but this is N is the number of cells in a culture after T time has passed on the stages of growth. And but it's the same. It's the initial E to the KT. And it's the growth rate of the cells that is K. It is always what? Positive. Always positive. Here we go. Then we have the uninhibited radioactive decay. This guy is the one that concerns most of our engineers or our scientists that deal with radioactive processes. You know, we get some part of our electricity. I don't know the percentage on that. Was it it's up in Pittsburgh, right? The 3, yeah, isn't it? It's up there. And they use radioactive material, so they're always worried about the usage of it and the happens from usage to deal with everything else. So we're going to see what we have here. A certain size P of a certain insect population at time t in days obeys the function P of t equals 700 e raised to the 9% times time being days. And this is growth, of course. So determine the number of insects at t is 0. At the initial, we know it's going to be t is 0, 700 e to the 9 times 0. So e to the 0 is 1. What is it? 700. Okay, on the B, it says, what is the growth rate of the insect population? And it is 9% per day. That is the K. The C, this is learning the components, if you will. What is the population after 10 days? Well, we would have P of 10 inserted. And we would use our handy dandy calculator, which I don't have activated. There it is. All right, I'm going to move it over here. I'm going to clear the screen and enter what I have, the 700 second ln for E to the decimal 09 times 10 and hit enter. And we don't have a part of a insect. And I think the computer, I'm not sure if we use the rounding rules for this or use the whole number, but I would say we have approximately, come on, Emma. We have approximately, after 10 days, 1722. But I think it'll accept either the 1721 or the 1722. Because this kind of an estimation, they give it a leeway. Is everybody comfortable with that? Okay. But I use rounding rules. So. All right. So C. Now D says, when will the insect population reach 840? What this is P of T equals 840. Okay? So I'm going to have to put the 840 equals the 700 E to the 9/10 T. All right. So we're going to divide by the 700, and then we'll do the natural log on both sides. Is everybody comfortable with that? Okay. After we multiply, we're going to use some rules. Let's say rules. Again, good for the review, right? So I'm going to divide by that 700. I'm not doing any math till the very end. Does everybody understand this? In mathematics, you don't simplify ever till the end. Ever, ever, ever. In science, in physics, that's why we make you buy very powerful calculators. Just so you know. So that'll cancel that guy. And so that leaves me the 840 over 700 equals E to the 09T. Well, I'm going to do natural log. Which leaves me what? Well, if I do an ln of E, they're inverses of each other, right? They cancel out, right? So I'm left with this guy. Correct? Now I'm going to divide that by 9/900. So now I'm going to stick it all in the calculator because this cancels, and I'm left with my approximation. Here we go. So we're going to do the natural log of 840 divided by the 700. And then we're going to take that and divide it by the 900s. Okay? And it's in days. How many days? Approximately. We can't say 3 because that would be overkill on expectations. Does that make sense? Right. So now let's see what the next one is. On E, it says, when will the insect population double. All right. So we're looking for time. So we're going to double the 700, right? Our initial. Divide by that 700 and get 2. We're going to take the natural log. Everybody comfortable with that? We're going to divide by the, oh, that's a 9. Sorry about that. Oh my God. Nobody caught me. It was a 9, but it looked like a 4 after I did it. What this? There we go. And then I'm going to divide by that. Get T. Okay, here we go. Now it's calculator. Natural log of 2, make sure you close your parentheses before division, okay? Otherwise you get a really weird answer. And you're going, why did I get it wrong? Okay, I forgot to mention that. Sorry. Oh, good? Yes. 8 days would be the safer. Questions on this problem?
So how did we do
Double? The double?
for part B?
Oh, B. Oh, we read the K. I wrote K value. The K in the problem. Okay, this is A of O times E K T. Well, K is our growth. That's a good question. I just assumed it's wrong of me, you know? That's wrong of me. Everybody good? That was a good question. Else that I went hastily over and I shouldn't have, or whatever. I have 7 problems, by the way, on this guy. Okay, they're not. I just need you exposed. Okay. On this one, we have radiation decay. Decay is the only time we have a negative on the K. According to the function A of T, according to time, the amount of this radioactive material, according to time, is decreasing how much? Okay, what is T here? T is in years. 44 hundredths, yeah, year. Not quite 2.5. Now, they're very explicit about this type of material because your life depends on it. So they will definitely go at least 3, sometimes 5. How dangerous it is to the environment. Okay, so here we go. Our A's of O is e to the negative 0.0244t, where A's of O is the initial amount and T is in years. And we already know what K is. It's decaying at 2 and 44 hundredths percent per year. All right, but I'll get to those answers in a minute. Assume the scientist has 800 grams of this particular radioactive material. So A's of O is 800. Okay, our K is negative 0.0244 per year. And that's all we need to know. Is everybody comfortable? All right. What is the decay rate of strontium? Thank you. 90. And we're going to say 2 and 4400% per year. How much of this radioactive stuff is left after 40 years? Here we have T equals 40. So on our B, we're going to put A of 40. And we're going to insert using our calculator on the home screen. There's no app. You could invent one, by the way, because these calculators you can program. You haven't met Mr. Blaskowitz. Boy, he's a whiz at programming these things. Okay, so we're going to enter our 800 second ln. We're going to enter the negative sign, decimal 0.244 times the 40. And making sure that it's all enclosed, whichever calculator you have. Mine displays it in the way it's shown on your paper. And I get 301 and 4522, blah, 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 blah. So, and we want to know how much is left. What would you say? 1 grams? I would say that. Everybody comfortable with that? All right. On our C, we have when will only 200 grams of this radioactive material exist? So my A of T is 200 grams. All right. So I'm going to have the 200 equivalent to the 800 times e to the negative negative 0.244. Don't we want to know how long it'll take to get to that? It will never, ever, you take half and half and half, you'll never get to the end. It'll always be a residue, like Chernobyl. It's still what a mess. And we always almost had that on our 3 Mile Island or whatever it is, wherever ours is. We had a heat problem. All right. So naturally, we're going to do the natural log on both sides. And then we're going to divide by our coefficient to the variable. Righty, are we good? Okay, I don't know what kind of answer we're going to get here, but we're going to be excited. I can do. Sure. It says 56 years. I sure would. I sure would. A certainty would be 57 years passing. You want it, all right. That's an M and an S. I'm at the bottom with this thing and it not work. Okay, now I'm going to do the D. What is the half-life of this radioactive material? So we're saying we want a half, and that would make it 400. Now we know that it reaches 200, approximately 57. Well, we know also that that is not, well, it's not going to be half of that. It's going to be like a year and a half less because each time it's decaying at 2%. So it might be in, oh, I don't know. Okay, it's 2%. I don't know. I'd be guessing wrong. So I'm going to have the 800. So we want half. So I'm going to have a half. I'm going to take the natural log. So I know it's a half. I'm going to divide by that number. Doing that, I'm going to then do my calculator. Like I said, it's not real difficult. I don't know if it is or it's not. I don't know. Off one of my zeros. Have that on the notes. Right. Questions on that? Unsightly? Other than now, I'm going to drop in the zero? Okay, that is unsightly. Okay, now this one, I copied the whole problem. The reason being that we hardly anything in the heading of it. And so I said, okay, I'll just write it out. This says if N is the population of a city and T is the time in years, express N as a function of T. And what this wants is the general formula. And I think on population, it's still A's of O. Yeah. And it says if the population doubled in size over 18 months, and it's in years. Okay, here we go. It's T is in year. We're talking here 18 months, and the current population is 9,000. So my N of T is 90,000. What will the population be 3 years from now? 3 years from now. That's what it is now. So this is going to be actually what we figure out our A's of O was, or use that. The population doubled in size over 18 months to the current population of this. What will be the population be after 3 years from now? All right. So I guess we could use it as our A's of O, because that's where our starting point is, where it's doubled after 18 months, but we don't have a rate. Does that make sense? Okay. All right. So let's do it. Okay. So we're going to say this, and we're going to find our rate, or K, because that's what we need. Okay. So I have 90,000 equals, and it doubled in size. So this is 45,000. E to the K times, what is 18 months in terms of years? All right. Is everybody comfortable with that? So I'm going to have the half over here. One and a half K. All right. I'm going to take the natural log. Put a half. It's fine. That's how I learned it. Okay. So now I'm going to divide by the 1.5 to find the K. All right, here I go. I don't think I can. Oh, yeah, I can. Whew. I was saying, ooh, I don't know if I can get this thing to move, because I copied it from the book. Here we go. So I'm going to stick that in my calculator. So I'm going to have the natural log of a half and I'm going to divide by the 1.5. Now let's see if I wrote it so that I would have the population is approximately, this one was easy. This one was 45,000. Okay, and then this one, oh, I'm sorry. I jumped the gun. I misread. I'm doing this part right there. Sorry. So what will be the population in 3 years from now? So now our population is 9,000, right? Because we figured out what the K is. I'm guessing we're going to do 3. I don't think it's 3, but thank you. I entered it. But hey, you call me on it. I mean, I don't know if to use 4600s or 462 thousandths. I'm going to do thousands, and I didn't find what they wanted, or I didn't write it down, I should say. Okay, so now I have my K, and then this is in 3. For that, oh wait, hold on, it's 990. Hold on, I'm not using the half. Okay, it says if the population doubled in 18 months and the current population is 90, I did that. What will be the population from now? Okay, so this is 90. Sorry about that. So sorry, so sorry. I don't want to tell you the wrong. It just looked funny, and I went, Alma. Going real big. Grows at almost half. That is a super boom. Okay, now we're talking half-life of radium is 1690 years. If 40 grams was present now, how much will be present in 180 years? So in this case, we're saying the years. Okay, that's what it's saying. Then it's saying if 40 grams are present now, how much will be present in 180 years? All right, so what are we missing? No, the half life is 169 years. Well, we got the T. Yes, the K. So I'm going to just write it as 1/2 equals the K times 1690. Oh my God. It's a lot of years. Okay, we're going to have a lot of decimals here. Maybe. I don't know. So we're going to do the natural log. Divide by that 1690. So let's see what we get. Okay, get my calculator out. We good? So we are decaying at negative, let me see if I did everything right. Natural log of 1/2, 1690, because we want our K, and it's a negative 4.101. Oh, to the 4. Oh, sorry about that. This e to the 4 means we have a lot of circles, zeros in the. So we're going to make it just the 4. I apologize. The e to the negative 4 is how many decimal movements to the left we're going. And all right. So how much will be present if it's right now at this amount? Okay. So now we have our A's of O is equal to 40 grams. Our T is 180 years. Our K, decay, is a negative 0.0004. And we want to know our A of T. So we're going to say A of that 180 equals our 40 E negative decimal 0.0004 180. Is everybody comfortable with that? We're going to put it in our calculator, just the way we see it. So we're going to say what? About 37? Yes? Okay. Any questions? I'm sorry. We had to first figure out what our K was and how to read the calculator when it says E to the negative. I almost missed that. I said, God, that's pretty high. And then we worked the problem. We could construct it with the original measurement of what they had. All right. So now we have, this is the one, carbon 14 is the standard. It's the golden rule. Life of carbon 14 is 5,600 years. In a piece of charcoal made from the wood of a tree shows only 73% of the carbon 14 expected in living matter. What did the tree, oh no, when did the tree die? All right. When did the tree die? A long time ago. And I don't think I put that carbon 14 rule. Let me look that one up. It's a specific, let me look it up. I don't know if I'm, a minute. Oh, Clint, look it up yourself. Yeah, look it up on yourself. And I mean, I'm going to look it up too because I omitted it from my notes. Everything else had the individual, but this one on carbon dating has, I think, a specific formula. What is? Okay, gotcha. I might have an easier one on the pre-cal book. Hold on. Sorry, I didn't stick that in there. I'm kind of Found it?
No, there's 7.
Oh, no. Oh, no. Okay, maybe we have to calculate it. Hold on. Okay. It says all radioactive substances have a specific half-life, which is the time required for half the radioactive substance to decay. Carbon dating uses the fact that all living organisms contain two kinds of carbon, carbon 12, which is stable, and carbon 14, radioactive carbon with a half-life of you can't see it, of 5,730 years. So carbon 14 has a half-life of 5730. And that's what they have. They have 5,600 years in a piece of carbon charcoal made from the wood. Only 73% of the carbon 14 expected is living. When did the tree die? We need time. Okay, got it. It's just a drop in. That's all. Okay. So here we have a half-life equals 5600 years. All right. And the piece of charcoal shows 73% of the carbon 14 expected in living matter. Okay, so that means that we have 100 minus a 73, and I get 27, right? So the K is 27 carbon in it. When did the tree die? So we have 27% of this carbon, not the half. So how am I going to work this? When did the tree die? So we need, okay, so we know half-life. We know this. Okay, and we know that time is 56, right? And we need the K. And I'm thinking we're going to have that 27 because we're having 5,600 K. First times the K. Would you agree? What do you think? Is that good logic? Okay. Then I'm going to have the natural log. We're looking for K. Okay, so I'm going to divide by that. I don't think I'm off too much. Let's do it this way. Ln of a half divided by the 56 for the half-life years. Oops. Sorry about that. 5600. Yes. So I'm going to have a negative decimal 1, 2, 3, 1, 2. So I'm going to put that. Is that okay? All right. So I know what K is. And now they're saying, now this is where it gets me. If a piece of charcoal made from wood of a tree shows 73% of the carbon 14 expected in living matter, when did the tree die? So we're talking time, and we're talking 27%. What do you think? Because now 50% is after 5,600 years, right? And so the percentage is negative 0.0001 per year. So it would be kind of like I'm getting 27% carbon dating, right? Did I do that math right? 73 minus 100? Okay, we're good. Natural log. Now we just stick it in a calculator. I think that's pretty. ln 0.27, because that's, we're going to divide by the negative decimal 1231. Right, higher than the half. Was it the 73 I put there? Let me read that again. I'm only having trouble with this. That part wrong. Everybody read with me. A piece of charcoal, that means it's already charcoal, made from the wood of a tree shows only 73% of the carbon expected. Oh, it is 73. It's 73. Sorry, I didn't have to subtract. I thought it was 27, which it's less than the half, because this is going to be 73 is what they have. Sorry. Bad thinking on Monday. Sorry. To do it again. I have to be intuitive in a sense. Much better. Because it's coal. It's already coal. So this is prehistoric, pretty much. All right. After the release of radioactive material into the atmosphere from a nuclear power plant in the country in 1983, the hay in the country was contaminated by radioactive isotope. Half-life 7 days. Safe to feed the hay to cows when 12% of the radioactive isotope remains. How long did the farmers need to wait to use this hay? I wouldn't use it. I would not use it. Oh my God. What a terrible problem. All right. Half life is 7 days. And it is safe to, after it reaches 12% of the radioactive remains. 12%. Right. So we've got our T, and we have the half, right? Now, where does a 12 come in? First, we have to do our K, because we don't have it. And to reach 12%, we're going to stick 12% as the output. Is that understood? Everybody good? All right. So we're going to have 7K, because we all know it's 7 days times whatever that decay is on this guy. Oh, 7K. Oh my goodness. We're going to do two nines. I feel terrible putting it at 10%. Okay. So we want 12% is equal to 099 T. This time we want time to reach that value. Is everybody comfortable with that? Calculator? Decimals, because sometimes my tablet doesn't show it clearly. It looks like 21 days. Like I said, I wouldn't feed it. I just destroy it. So what we do with the chickens that got that disease. Destroy them. Nobody can eat them. Okay, everybody good? Okay.